Part 2 of Kirchhoff's laws, grade 12 college prep physics, looking at examples of parallel circuits. Here's the picture. You have this picture in front of you, I'm sure. Just to be clear what we're looking at, we have 3 motors that are in parallel with some battery or something. We know that looks like a 9-volt battery to me, and we know the total current coming out, okay, of our battery. We also maybe have placed an ammeter and we know I1 and I2, okay? And we're looking for everything else we don't know. So we're looking for the volts on all the loads, and we're looking for the current through the third load. So just to solve something like that, not too hard, first you apply the fact that being a parallel circuit, the potential difference, the voltage, whatever, across each motor, the energy used per electron, across each motor is the same. And in this case, the voltage then is 9 volts. So V1, V2, and V3, we know them all. They're 9 volts. And so we know that, we know that, we know that. And in order to find I3, use the other thing we know about parallel circuits, which is that the total current is equal to the sum of the current down each branch. So we know the total current. We know these two currents. We're just looking for I3. Oh, I said I2, but that was actually a mistake. Either way, the current we don't know, which is actually should be 3, is 1 amp. Okay. Now looking at resistance. Now resistance is, remember, that's how much each load slows down the current, and then the equivalent resistance or total resistance, use either term, is sort of the total for the whole circuit. If you can't say just add up, but it's sort of how much every amp is slowed down. So applying Kirchhoff's laws, it's a terrible circle job I did there. What we know about a series circuit is that the voltage across the battery or the power source is equal to the sum of how much energy is used per coulomb for every part of the circuit. Okay? But we also know from the beginning of the lesson, the resistance lesson on Ohm's law, this relationship, that volts equals current times amp. So if I took this relationship, and by the way, you don't have to regurgitate this for me, this is just for your information. If I took all the V's and replaced them with I's and R's, then I know this. And the reason I'm doing that is, again, I'm looking to figure out how do I know what the total resistance across a series circuit is. Well, if we cancel out the I's because they're all the same, then this is my equation. And I put the dot, dot, dot because, in my picture, I draw 3 loads, but there could be 8 loads, there could be 12 loads, there could be 2 loads. I just, I do 3. Okay. In a parallel circuit, same thing, 3 loads, but this time in parallel, and I want to find RT, an expression for RT. It's not just the sum. It's more complicated. We know the current, IT, is the sum of the 3. And from Ohm's law, I know that current equals volts divided by resistance. So if I took out all the I's out of this and replaced it with V's and R's, I have this expression. But because the V's are constant, they cancel, and then this becomes the equation, which is significantly different, and you'll see that in our example in a sec. So say we have 2 circuits. They're both wired up with the same resistors. One of them is wired in series, the other is wired in parallel, and I wanted to find the equivalent resistance. Okay? Well, in the series circuit, all you got to do is add up the 3 resistors, so the equivalent resistance is 35 ohms. In the parallel circuit, this equation, your instinct might be, can't I just flip everything? And mathematically that's not correct. You can't just flip it, and then if you did, then the total resistance would be 35, it'd be the same. But if you follow the, what I've done here is just 1 over 10 is 0.1, 1 over 5 is 0.2, 1 over 20 is this. So 1 over RT is 0.35. Then you do 1 over 0.35 and find out that that's 2.9 ohms. And that's the total resistance, which means that a series circuit has higher overall resistance, which is not usually better, not often better. Okay. Now all the information I've told you, we can put that all together and look at a circuit, and this is not a very good circuit diagram, but it's a picture of, and there's lots of things you can know about the circuit. You can know the current through every single load. You can, and the power source, you could look at the volts and the resistance. So there's three things, but there's three things we could know, and there's three things, but they apply to, in this case, 4 different parts of the circuit. And if we know some of the things, in this case, we know all resistances, and for some reason, maybe we stuck an ammeter right here, and we know, or right here, I guess, and we know I1 was 5 amps. Could we find all these other things? Okay. Well, the first thing is to consider what strategy do you follow to do that, because it looks like a lot of stuff. But if you take the information I've told you, starting with Ohm's law, and there's the 3 versions of it right here, right? And you take what I told you about current, voltage, and resistance around a series circuit, you can pretty much solve for everything you need. And so we want to find everything about this circuit. So looking at the solution, first of all, you say, okay, by the way, a great place to start again is if you know 2 things about any one part. In this case, in the first bulb, we know the first amp and we know the first resistance. Then just use V equals IR. So now we know all 3 things about that first bulb. The other thing we know is that because this is a series circuit, you know that the current is constant. So we know all our I's. So we know V1 now, we know all the I's. We also know that the total resistance is the sum of all the resistors, so we know the total resistance. So that's sort of the strategy you take. You just take, you start, it's like a little bit of a logic puzzle. You look at what you know and what you can do. Right away, if you know 2 things about any one part of the circuit, find the third using Ohm's law. That's the best start. And then look at, okay, total current, total resistance, total volts for the circuit, and start figuring out what you can do. At this point, we know 2 things about V2 and V3, so we can find, or load 2 and load 3, so we can find V2 and V3. Okay, so you might need to pause, but I'm going to keep moving on. That's solving a series circuit, and our last example today is solving a parallel circuit. Okay, so here, this is not a very good picture, but you got some battery, some source of power, right? So that's going to be our T. Our IT, RT, VT will apply here. This is R1, R2, and R3, and this we're just saying they're resistors. And we know it's 120 volts. We know the voltage across, and we also know the individual resistances. And we're asked to find everything else about this circuit. So there's a couple places you could start, and if you're thinking yourself of what to do, that's perfect. You should be thinking of a strategy you would follow, because obviously you'll have to solve some questions like this. The way I chose to start, and it's not the only way you could have started, but I chose to find the RT by applying Kirchhoff's resistance rule, okay? Because I know all the resistances, I can find the last one using Kirchhoff's, okay? And then I could say, okay, then if I know resistance and I know RT, I know VT, I can find IT. That was the second step I took. And I say it again, that following the same order than me is not important. I know looking at this, there's a different path we could have followed. Just going up here, one thing I know is the parallel circuits, the volts are constant. So something I could have done right away is said R1, R2, and R3 are all equal to VT, right? Which is what I did here. So you could have started with this. I put it as the third step. It doesn't matter, okay? But the thing is now that I know all my V's, I know my RT, I know everything, all I gotta do is look at, I know 2 things about all my resistors. I know the volts and the resistance, so I can solve for the I's. Okay? And that's how you solve a parallel circuit. And that's a pretty tough problem. It takes a few steps, right? But if you're diligent and there's not that many things you need to remember, you should be good to go.